Okay, so today I'm going to try my best to clear up some false information, just misunderstandings. The internet's great until a rumor gets started or something that's not accurate, and it spreads like wildfire. And, I mean, this happens even without the internet, but it's just so much more prolific nowadays. In the old days, something was wrong, you told somebody, they'd think it was correct and they'd spread it to the next person and the next person. Nowadays, you just type it on a computer and bam, the entire planet can see it. And if it's not correct, then everybody on the planet's spreading it. So what brought this on? Someone contacted me. I'm not going to use any names here, no YouTube accounts, no websites, no nothing. I don't like calling people out. It just, I don't want to say inappropriate. It's just not nice. But there are some people on YouTube, and it's not that they're, well, I don't even know how to say this. I've tried to do this video a couple times and usually end up in a rant. So I'm trying to keep myself calm and not get into rant mode. I don't think they're intentionally trying, well, some people are intentionally fooling people. They're good salesmen. That's basically what it comes down to. Other people, I think, just don't have an understanding of what we're going to be covering. And as you saw in the title, it's voltage, power measurements, and measuring receiver sensitivity. I haven't decided exactly what I'm going to make the title yet, but try and get all those keywords and whatnot in there. And like I said, I think some of it's just a plain lack of understanding. I know some of it is because, and I'll show that here. It's one of the first things we're going to go over are measurements, or at least different methods of writing down the same power or voltage readings. And you can misinterpret them if you don't understand how they work. Other things are when you get into receiver sensitivity, well, we'll cover that when I get to it. I'm, like I said, trying to keep myself calm, don't want to get into rant mode. So, for starters, there are numerous ways that you can express voltage or power measurements. Lots of different ways of writing that down. And if you don't understand those exact measurements and what their reference is, you can get mistaken and then convert that into another measurement type that's wrong, or your end result is wrong. And so what I actually saw, because I've had videos forwarded to me, I've had people emailing me, asking me stuff about this. Now, I did a video. Feel free to go back and look at that one, because that's actually going to cover it a lot more in detail. But S-meters. What is S9? So if you go back in my videos a year or more, I think it's been quite a while since I did that video. But what is S9 on a signal meter? So you've got a radio, something like that right there. What is S9? So when we do an alignment on a radio, one of the last things you do when you're doing the receiver alignment is you calibrate the S-meter on the radio. Now, pretty much all S-meters are inherently inaccurate anywhere except at S9. Good radios are more accurate over that entire range of the meter, where radios that have less accurate S-meters, which unfortunately is a large majority of them, the farther you get off of S9, the more inaccurate it is, because they're not linear. So, the actual power level that should indicate S1, S2, S3, S4, S5, 6, 7, 8, 9, and then S9 plus 10 dB or 20, 30, 40, 50, and so on. If you calibrate the meter at S9, that's really the only place where it's truly accurate. Anywhere else below that or anywhere else above that isn't quite right, and the worse they are, the more out of whack they get, the farther away from S9 you get. But there's, for starters, some false info, I guess, being put out there that, there's all these different standards for amateur radios are different than CB radios, are different than, all different forms, military radios and, other communications industries and whatnot. Nah, pretty much it's just, there's two international standards. Been around for a long time. There's an S-meter chart for frequencies below 30 megahertz, and a frequency chart for or an S meter chart for frequencies above 30 megahertz. I suggest you go back and look at the video I did on S meters, where, like I said, I covered specifically just the S meters there. But you can see there's lots of different ways, and I've even written in some here, you know. So the problem is, in the video that I saw was, this person says that S9 on a signal meter is minus 67 dBm. That's not correct. And then we're talking about a CB or 10 meter or an export radio here. But actually, any radio below 30 megahertz, you would use this chart. Any radio above 30 megahertz would be this chart. And the reason there are two different charts is there's more noise at 30 megahertz and below than there is at 30 megahertz and above. The higher you get in frequency, the less background noise there is. It's just a fact of RF life. So you don't need as big of a signal to be able to hear it above 30 megahertz. Like I say, the higher you get, the better it gets, than you do with 30 megahertz and below, where it's extremely noisy, just all kinds of noise in the background. You know, from galactic noise to noise being generated in the radio, from like cross modulation inside the radio. You know, power supplies, especially nowadays, switch mode power supplies and whatnot. But like I say, so there's two charts. But, you know, S9 is minus, let's get the camera down here. Of course, I've got these laminated, so of course they, they have a glare to them. But S9 is minus 73 dBm. It is not minus 67 dBm. Now, the person in the same sentence said minus 67 dBm or 100 microvolts. Aha, you gave another reference, 100 microvolts. Now, that would be correct, but that's 100 microvolts, and I had to write that one on this chart. That's EMF, or electromagnetic force, or electromotive force. And if you go watch that one that I did where I explain this a little bit more in detail, I even show that on a communications test set where I can punch in 100 microvolts EMF into it. And then I hit a button on there and it does the calculation for you, and it will switch between all these different measurement styles. But you'll see 100 microvolts EMF or 50 microvolts, but that's terminated. And we're going to cover this, you know, actually let's just grab the chart. But I know where his mistake is. If we look at a chart here, and you can see, glare again killing me, focus, 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 minus 67, 100 microvolts. Aha! He probably used a chart like this. So he saw in a service manual where it said 100 microvolts for an S9 reading. Well, that would be correct. But the problem is, that's 100 microvolts open. That's non-terminated. There's no termination. There's no load. It's, you know, and minus 60. There's minus 67 is 100 microvolts. But like I say, this chart is 50 ohm system. Okay. This is an EMF voltage. You know, 50 microvolts. If we look again at this chart. Focus, focus, focus. We look at 50 microvolts. Aha! Minus 73. He saw 100 microvolts in the service manual and figured that meant minus 67 dBm. No, no. When they give in service manuals, you'll usually see that, especially in older service manuals. You'll see them give the signal level required for S9 as a microvolt reading, and it will say 100 microvolts. But they're not talking about a 50 ohm system. That's 100 microvolts unterminated. The instant you put 50 ohm load on 100 microvolts, it actually becomes 50 microvolts, and it's minus 73 dBm. So let's cover different methods of measuring or expressing power and voltage. And there's a lot of them on here. So these are methods we have of several of the different ways we have of expressing power and several of the ways that we have of expressing voltage. So all of these are exactly the same thing. You can take any one of these and convert it into any of the other measurements. Every single thing that's written down here is the exact same power level. You could put out a minus 73 dBm signal out of a signal generator or whatever you're using, And you would be able to measure this, depending what type of meter or power spectrum analyzer or power meter or voltmeter, what you're using. You could get, but these would be the numbers that you would come up with. So minus 73 dBm, but here's the key ones. Minus 73 dBm is equivalent to 50 microvolts, okay? But it's also equivalent to 100 microvolts. But notice that this says EMF, okay? That's our electromotive force. This one, and that's the nice thing about dBMs. When we use dBMs, dBm is always, there's no exception, it's always referenced to a 50 ohm load. When you express something in microvolts, when you say it, you actually should be telling at what load, or is it unterminated? You need to know that, because if you change the load, it's going to change the voltage, because more voltage is going to be dropped across the load. But yeah, these are all the different ways you can express it. So if we go down here, I can show this. And this is a little bit more of the definitions of it. So microvolts, PD. So this is going to be a terminated load. And you can express, and you'll notice up here I have microvolts, and I also have microvolts PD. And you'll see they both are the exact same thing. It's because they are the same thing. It's just one of them is specifying. Where this one you're kind of left wondering, 50 microvolts, what? Terminated or unterminated? You don't know. Using microvolts PD, you know it's a terminated system. That measurement is taken 50 microvolts terminated. So 50 microvolts PD. This is the value in microvolts with a load. When a signal has a matched load, then half of the voltage is dropped across the load. This value is expressed the same as microvolts. So in a nutshell, that says it's expressed the same as microvolts. So that's why these two numbers are the same. The unit is just explicitly defined as having a load. And what it means by that is that PD explicitly defines that that measurement was taken with a load. And mathematically, here's how you would come up with that. So if we look up here at our little chart, we need one thing to calculate microvolts PD. We need the volts peak. So 0.0000708 volts voltage peak is all you need to calculate microvolts terminated. So if we turn on a calculator here, so we want fraction, we want the voltage peak, which is 0.0000708. And 2 times 10 to minus 6th equals. And you can see we have 5006 blah blah blah. So 50, and then it's rounded up. You'll usually see it when you do conversions, and a lot of times you'll see like 50.1. That's actually rounded up because 6 is higher than, it's more than half. 5 and 6 are the break point for when you're rounding numbers. But 5.006, and this is 6316011 times 10 to the minus 11th. With if you move the decimal point over, that comes out to 50 microvolts, or 50 point. It's actually 50.0631611. But like I say, they just round it up. So whatever the last digit is, they'll round it up or down depending. But that's how it's calculated. That's all you need. Take a voltage measurement, and you can transform that into a terminated measurement. Another way is EMF. So EMF, remember, is unterminated. So that's just like taking something out of a signal generator up here, but nothing attached to it. And actually, that signal generator right there is a good example. That has the output attenuator knob on that is actually calibrated in 2 scales, decibel or dBm, but it's also calibrated in microvolts. But the microvolt, because that instrument was specifically designed to be used with CB radios, and CB radios, for the most part, there are a few exceptions in service manuals, but for the most part, all CB service manuals usually specify S9 at 100 microvolts. Now, That used to confuse me because I thought 100 microvolts. It's the same thing. This person with the minus 67 dBm didn't know. I did a little bit of research and I found out the information. But that's why it has the microvolt scale on that is calibrated unterminated, is because B&K knew that that's the way most CB service manuals are written. So they were trying to prevent confusion. So that one, when you look at it, minus 73 dBm is 100 microvolts. They're, two numbers side by side for the same level. But like I say, they just tried to clear that up. But calculating microvolts unterminated, another formula here. So if we were to take again 2, now this time you can see. Okay, this was just the voltage peak. This time we need to actually multiply the peak by 2. So 2 times 0.1234708 and again times 10 to the minus 6 equals. And you can see our EMF, microvolts EMF, 1.001 blah 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 blah, but times 10 to the minus 10. So move the decimal place over 2 times, that's microvolts. So 100.1263202 microvolts. But again, 0.000, well, I'm out of view there, 0.000708 is 50 microvolts, and it's 100 microvolts. But it depends on which you're either measuring it into a terminated load. And what they mean by that is the signal generator is attached to the radio, because the majority of the radios you're going to work on have a 50 ohm terminator. That's just the load of the radio. It's 50 ohms. Your signal generators, the output impedance on the signal generator is 50 ohms. You're using 50 ohm coax cables. And then, of course, we have our dBm. dBm is the power, and is the decibel of the power in milliwatts. So that's all dBm is. dBm is the power measurement. It's not a voltage measurement. It's a power measurement. That's another thing to be clear. These are power measurements over here. This is voltage, even though they mean the same thing, but still, this is power. These are voltage measurements, because you won't see any microvolt. You'll see nothing voltage over here. Everything you see over here, because we're measuring power, is either ending with a W, watt, micro, pico watts, whatever it might be, milliwatts, watts, and or dBm. But so that's the difference. Like I say, it just kind of irks me that the information is so easy to find out there online. Good Lord, there's probably hundreds of websites where you can get this information. Any RF book, if you pick up any RF book, you can get all of this information. It's in there. Get yourself an ARRL guide. I mean, good Lord, people, you're going to do this and I'm not talking about the average Joe using a radio. You don't really need to know all this stuff. But if you work on radios for a living, and you're going to be posting videos or posting stuff in messages online, whatever, you need to make sure that you get your information straight, because if you don't, you're going to be spreading information that's false. Minus 67 dBm is not 50 microvolts or 100 microvolts. 50 microvolts terminated or 100 microvolts non-terminated. Minus 67 dBm would be 100 microvolts terminated. So, like I said, just be careful. And you can just download these little charts online too. I didn't have to make these up. These are online. Just type in S points for frequencies, chart, and you'll come up with these 2 charts. And then if you go to mini circuits has the decibels or dBm to volts and watts conversion chart on their website. Now, of course, I expanded this one up on the top end because it stops at plus 53 dBm. And I continued it up to plus 60 dBm. Now, another thing is actually how you say it. In videos I've seen, and actually not just this person, I've seen other people say it this way. They'll say 67 dB down. That's not correct. Or even if they're using the correct number. But you would not express this as 73 dBm down. No, that's not the correct way to say it. You can use down when you're using it in basically relative to something else. So if you take a measurement with a spectrum analyzer, and this is good if you're measuring adjacent channel splatter, or a sideband compared to a carrier in a modulated signal or something. If you measure the peak of the carrier is at, let's say, 20 dB, and the peak of the sideband is at, let's say, minus 10 dBm. Well, the difference between that plus 20 dBm signal and the minus 10 dBm signal is 30 dBm difference. So you could say it's 30 dB down, or minus 30 dBm down. But yeah, like I say, that's where you would use the down, because you're referencing it to something. And that's the thing you got to be careful with when you're doing stating measurements. You need the reference. What is that reference to? Because as we just showed, if you don't know, that's why I don't like it when people just write microvolts. You don't know if that's terminated or not. Where if you write EMF or PD, you know it's either non-terminated or terminated. You just need to be really clear and careful with how you say things, because it can get really confusing really fast if you don't know what things are being referenced to. So I think that pretty much covers that. I'm not going to go over that anymore. Like I can talk for. I don't want to make this video too long. I know it's going to end up over an hour. This was actually the last time I tried to shoot this video. I didn't even cover this as in-depth, but I thought I should, and I should show some of the different methods of expressing voltage and power measurements, and actually what some of them mean mathematically. And all you need is a calculator, scientific calculator. It's all you need to calculate this stuff. You don't even need to understand the formulas, honestly. That's the one great thing about math nowadays. If you own a scientific calculator, now I highly suggest you study the math to understand what it means. But if you can look at that and you know that you need to insert something like 0.0000708 into the formula to come up with the end result, as long as you know how to use something like a scientific calculator and you can put those numbers into the calculator, it'll do the hard stuff for you. You don't even need to know how to do it. Just let the calculator do it for you. And especially if you're going to be doing it a lot, you'll learn it. I've seen people that do that have a hard time understanding math. No matter how much it's explained to them, how much it's simplified, or different examples are given on how to do a certain formula or what different symbols mean. But when they do it for a while, they'll use a scientific calculator. Eventually the light bulb goes off one day. They go, all this time I didn't understand, and that's what that means. They finally realize maybe what an exponent. Okay, moving the decimal place. The light bulb, they have a light bulb moment. But yeah, the scientific calculator, great tool to have. So I'm going to pause the video here, and I'll get a couple more pieces of paper out. Give me a chance to get a cup of coffee before my throat dries out here. And we'll cover some of the different methods of receiver sensitivity, what they mean, how they're measured, differences between them, which ones are some of them better than others. And after I get done that, I'll probably pause the video again, and then I'll do a final section where I'll just go, I don't know what the heck I'll use. I'll just go grab a radio off the shelf. I've got, I'm surrounded by them. But I'll just go grab a radio off the shelf, something that has not had an alignment to it yet. Probably an old radio maybe. But we'll take some sensitivity measurements, and I can actually show that with instrumentation and what that means and how it's actually done. So let me pause the video here, and I'll be back, and we can get into what is or are some of the different methods of measuring receiver sensitivity. Okay, so we're back, and we're going to start talking about receiver sensitivity. For starters, there are some claims out there you'll see sometimes, people with just honestly unbelievable sensitivity measurements. There's just no way a radio can receive so good. Now, I've had radios on my bench that were just phenomenal receivers. But still, they could not receive anywhere close to what some of the stuff that I hear online occasionally, some of the measurements that are being given. Sometimes those measurements are not being taken correctly. They're not being, again, we need that reference level. In reference to what? Or what is the industry standard? You can't just go making up random specs for a radio. If you want to compare apples to apples, oranges to oranges. You know, it's hard to compare, let's say, the vacuum tube that's in this box with this little digital variable gain amplifier here. It's two completely different things. Yeah, they're both electronic devices, but, you know, this is a complete circuit. Got lots of parts on it, you know, powered. This is just a tube. You know, now if I had another tube, yes, then you could compare tube to tube. Or if you had two little amplifier boards, then you could compare an amplifier board to an amplifier board. You're doing, well, it's the same thing when you take measurements. You need to know what are the industry standards. And some of the problems that you run into with receiver sensitivity and what causes it, why is there a limit? Well, for starters, there's noise. So noise is just a fact of life. I'm not going to say there's nothing we can do about it. There's a lot of filtering that we can do to get rid of noise and get rid of that hash and trash, you know, adjacent channel splatter. There's a lot of things we can do to quiet up a receiver, but still, you can only do so much. And, you know, so this little hand-drawn squiggly chart right here represents, if you were looking at something like a spectrum analyzer, let's say. So you'd be looking at a signal. So this is our amplitude, and then from one side to the other is a frequency range. You know, you could have it at 10 kilohertz wide, or 100 kilohertz, or a megahertz, or 10 megahertz. But you know, this is the range of the frequency. So you know, this peak is at a specific frequency on this chart, and then the peak up here, that's your amplitude, and you can see the down here, these are at a much lower level or lower amplitude, so lower power or lower voltage reading. But what we want is this big peak. This is the signal that we actually want to hear. That's the person we're talking to on the other end, you know, wherever they might be on the planet. This down here is what we don't want. This is the noise that we don't want to hear, because if this noise level gets up too high, and especially when you're starting to get farther and farther apart from somebody, so you know, if you're talking to somebody in a mobile and you're talking on a base station as they drive away from you, the signal is going to get lower and lower and lower and lower. Your noise floor is going to stay about the same, but their signal is going to get weaker and weaker as they get farther away from you, and if they're getting closer to you, the signal strength is going to get stronger. But once it gets down to a certain point, you start having problems actually hearing what that person's saying, because they're getting lost in this noise. Now, like I say, there's lots of different types of noises. So there's RF electrical noise, there's avalanche noise, flicker noise, or 1F noise, phase noise, shot noise, burst noise, thermal noise. There's so much noise. You know, there's galactic noise, but a big one is thermal noise. So back in the, God, what was that? Long time ago, 1920s, I think. It's been so long since I read that in a book, I can't remember anymore. I'd have to look it up. 1920s, I think. Johnson basically discovered what is known as, nowadays is known as, there are three ways it's known. It's either known as the Johnson noise, the Nyquist noise, or more commonly referred to as the Johnson-Nyquist noise, because it was kind of a joint thing. Johnson discovered it, and Nyquist basically mathematically expressed what it was. But that's thermal noise. Anytime you get something above absolute zero, you got to remember, matter or thermal energy is movement of the atoms, okay? And anything above absolute zero, there's movement. So you're going to have this thermal noise. Now, us, with the kind of radios we use, there's really nothing we can do about that. It's just there, unless you plan on investing probably hundreds of thousands, if not tens of millions of dollars in some type of supercooling system where you can get your radio's receiver down as close to absolute zero as you can. There's really not a lot we can do about that. And some of these receiver sensitivity measurements that I see people saying that they can get a receiver down to are lower than what NASA can hear. So we're talking, and you feel Dave Jones actually was just at one of the NASA sites here, I think within the last year. posted a video, EEV blog, here on YouTube, Dave Jones. He went to one of the, I think that was actually a satellite station. I think that one was in Australia. Might have been a NASA station, but I think that was in Australia. Could have been in the U.S., I don't know. But in any case, the point is, they're using a huge satellite dish, and they've got a building filled with some of the, honestly, the smartest people on the planet when it comes to receiving signals. When it comes to RF communications, these are the people just at the top of their game, working with the most advanced and up-to-date technology, and even they can only hear a signal so low. Once it gets to a certain point, they can't hear it anymore. And like I said, they're using supercooling to be able to get their receiver sensitivity down to the point where it is, because they run into that. It's a roadblock. You hit that thermal noise floor, there's just nothing you can do about it without cooling down everything to below, as close to absolute zero as you can get. So, just really covered some of that. But the different methods. So, receiver sensitivity. If you're looking in service manuals, or even if you look in owner's manuals, a lot of times they'll have specifications in there, and they'll, like I say, there's industry standards, and then unfortunately in the CB world you'll see a lot of manufacturers will have it at different, they're taking the measurement at different levels, which they really shouldn't do. They should be using the industry standards. That's why there are standards. That way you can, like I just said, you can compare apples to apples, oranges to oranges, or a potato. It's kind of hard to compare a potato to an orange. They're completely different. One grows above ground, one grows below ground. Well, if you're not using the same standard, it's hard to compare those together. So the common ones you're going to see with CB radios especially, actually most two-way amateur radios, CB radios, business band radios, stuff like that, you're going to see signal plus noise to noise ratio and SINAD or SINAD. Honestly, I'm not 100% sure how that's pronounced. My entire life, I've either said it one way or the other, and in the same sentence, I might say SINAD, and then a second later say SINAD. I'm pretty sure it's SINAD, but as long as we understand what we're talking about, the way I pronounce it's not really important. So, receiver sensitivity. Signal plus noise to noise, or over noise. So that's signal plus noise to noise ratio. And it's also, occasionally you'll see that referred to in manuals as SNR, or signal noise ratio. It's just a mathematical equation. And the S plus N is not something you would be doing with a calculator. That's just a measurement of the signal and noise. So, but exactly what is this and how do we measure it? So, this check measures the weakest usable signal level at which the receiver will operate. It is a good overall check of a receiver's performance, and it is. This standard has been around for decades, probably longer than most people watching this video. You can go back into old manuals, and you're still going to see signal plus noise to noise ratio. That measurement standard has been around a long time. Receiver sensitivity is expressed as a signal level required to produce a 10 dB signal to noise ratio. Or, to be more technically accurate, signal plus noise to noise, because that's what that is. Signal plus noise to or over, because that's a divide by or fraction there, noise. So, an example. If you were to look in a service manual, you could commonly see something like this. 1 microvolt 4, and that's our magic 10 dB, signal plus noise to noise ratio. That's the standard, let's say. So, this means that a 1 microvolt modulated signal into the receiver's input should produce an audio output at least 10 dB above the receiver's noise level, obtained with a 1 microvolt input signal without modulation. Now, another thing when you see this in a service manual, the specification is usually going to be shown in service literature or specifications. Will usually state the signal plus noise to noise at a specified audio level, so something like a half watt or a watt of audio power. They don't want, in other words, they don't want the volume on the radio turned down too far, or it might not, you might not be taking a measurement of the actual true performance of the radio. You also don't want to turn the volume up the entire way, because pretty much any radio, if you turn the volume up full clockwise rotation, you're going to get a lot of audio distortion out of the audio amplifier circuit because it's saturated. You've actually reached a point where it's now horribly distorting a signal. So they'll pick, usually, like I say, they'll usually be around a 0.5 watt or a 1 watt reference level. And like I said, that'll be in the service literature. So, but what does that mean? So the signal, okay, right here was the key. It's the modulation. You either have it or you don't. So the signal plus noise to noise ratio. So this means, and we'll just read this again. This means that a 1 microvolt modulated signal into the receiver's input should produce an audio output at least 10 dB above the receiver's noise level obtained with a 1 microvolt input signal without modulation. It's real simple to do this measurement. Everything you need to know is right there in that sentence. So if the radio's specification is the receiver must be able to obtain 1 microvolt for 10 dB signal plus noise to noise ratio, what you would do is you would hook your radio up, you would inject 1 microvolt of RF signal. So let's say you're working on a CB radio on channel 19 or 20, because those are usually going to be you're usually going to check on the center frequency of a band. So you would inject, let's say, 1 microvolt at 27.185 megahertz for channel 19. You're going to then take a measurement. Now, I have several instruments here that will do it, communications test sets. I've got the old B&K 1040 CB Service Master over there. That meter over there will measure in decibels, has a dB scale. You don't really need anything more than something like that, just an AC microvolt meter or millivolt meter. But it has scales calibrated in decibels. So, and that measurement is actually taken at the speaker. So you'd be basically hooking up your voltmeter. If you're using, let's say, that millivolt meter, you'd be measuring at the speaker. And usually what I do, it makes it easier, is you would put the input signal so it's the needle rests right on 0. And then all you do is, because remember, the other half of that measurement is with a modulated signal. So without modulation, that's your noise. That's your end measurement. Okay, so that's actually what you're taking. When you inject a 1 microvolt signal into the radio, you're taking that measurement right there. And then you turn on your modulation. It's usually going to be, for most radios, it's going to be 1 kilohertz audio tone, because that's kind of the center of the voice range. And they'll tell you 30% modulation. So you would turn on the modulation on your signal generator, and without touching the volume control, you would take another measurement on your voltmeter. And it's, like I say, it has a caliber. You're not actually taking a voltage measurement. What you're looking at is that dB scale, or like I say, if I have the 1040 over there, it's got a dB scale on the bottom. But what you would be looking for is, remember, we had set the needle at 0 dB, and we want to see it increase at least 10 dB. That's what you're looking for. As long as it increase, the difference between an unmodulated signal and modulated signal at 1 microvolt, as long as you get an increase of 10 dB or more, you're good to go. Or if you took your signal plus noise measurement first, and you set your needle to 0 with the injecting the signal modulated, and then you turn off the modulation, it should not decrease more than 10 dB. There's a 10 dB difference between that. That's all that is. And like I say, it's been around for years, and manufacturers still use this specification. Another common one, and it has not been around anywhere close to as long as signal plus noise to noise ratio, is SINAD. So, SINAD, and this is always measured in dB, is the signal plus noise plus distortion divided by noise and distortion. I prefer this one because this takes into account distortion, where this one doesn't. So if your audio amplifier in your radio is causing possibly the frequency to shift slightly, this one is not going to account for that. If you inject a pure 1000 hertz modulated tone into a radio, if the audio amplifier circuit, or any circuit in a radio, is causing audio distortion, this measurement won't account for that. This does. So SINAD, for starters, can never be less than 1 dB. That's just the way the math works out. And it's commonly agreed, so this is basically the industry standard, that a minimum level for intelligible speech in two-way communications is 12 dB SINAD. The higher, the better. So, but that's our reference, 10 dB. Now, I see people on YouTube all the time expressing this measurement or 12 dB is the standard, but you'll see them saying, I get however many microvolts at 10 dB, or you'll see them say at 20 dB. And honestly, if you look in service manuals, and here's where the problem comes in, you even look in a lot of the specifications, you'll frequently see manufacturers quote their SINAD measurement at something like 10 dB or 20 dB SINAD. Now, you can no longer, again, you can't compare apples to apples, oranges to oranges. It's not a direct comparison. Where if everybody used the industry standard, and it's usually only CB radios where you see this, where manufacturers will have different levels that they're taking that SINAD measurement at. I think they almost purposefully do that, is it makes it hard for you to then compare one radio to another just looking at the specifications. And usually, honestly, their specifications they have in their manuals are accurate, or they're very close. But like I say, 12 dB is the industry standard. So when you express a SINAD measurement, you should always be looking for that magic 12 dB. So let me just move my block out of the way there. So the SINAD measurement measures the modulated audio output of a receiver at the speaker, just like we did with the signal plus noise to noise ratio, which is the signal plus the noise plus the distortion. The signal then passes through a notch filter, usually 1 kilohertz. Now I say usually, but I've never seen SINAD expressed in or used anything but the 1 kilohertz audio tone. But you often see that, usually in definitions. But like I said, I've never seen it in anything other than a 1 kilohertz audio tone. And it's measured again. This measurement is the noise plus distortion. So basically all this, and now this is something you can do with a meter that has a dB scale. You don't need any fancy test equipment to do this measurement up here. Like I said, you just need the signal. You need your signal generator. Needs to be able to produce, have modulation. But to actually take the measurement, you don't need anything more than an AC millivolt meter that has a dB scale, or like I say, BK1040 over there, it has a calibrated dB scale. But that's it. No fancy test equipment. To take a SINAD measurement, you need a dedicated instrument. So I've got SINAD meters made by Helper Instruments. I've got another one made by Motorola, and I've got pretty much every single, and I've got, God, I've lost count now. What, 1, 2, 3, 4, 5, 6, 7, 8, 9? I guess I'm up to 9 communications test sets, I think. Every single one of those takes SINAD measurement. But you need a special instrument for it because it actually has it has filters built into it. But what that meter is actually doing is it's measuring, so again, like it's up here I said where it's attached to the speaker. So you just take the SINAD meter, and they're very simple to use. That's all there is. There's just, especially like the Motorola, there's just 2 jacks. There's a red jack and a black jack on the front of it. You just hook up a pair of meter test leads to it, and you attach that to the speaker. It's just that. That's it. You just hook the meter up to the speaker in the radio. But what it does is it takes a measurement of the signal, because what it's measuring at the speaker now is going to be, and again, just like up here, you're going to be injecting a signal out of a signal generator, communications test set, whatever you're using. You're going to inject a carrier modulated with 1 kilohertz audio tone into the radio. The radio is going to demodulate that. It's going to end up going through the audio amplifier, and it's going to be measured at the speaker. But that measurement is the signal that you want to hear, that 1 kilohertz audio tone, but it's also going to include noise. And like I say, this one includes distortion. And I don't mean distortion as it sounds crunchy. The distortion is actually the frequencies actually changing. So that's why it has, and the way it does it is, after it takes this measurement, it passes it through a notch filter. So a notch filter, If you're familiar with the filters that are normally used inside of a radio, those are bandpass filters. So they're usually going to, like the crystal filter in your sideband circuits or whatnot, they only allow a small portion of the frequency through. So, let's say only that frequency. They're a band pass. They only allow a certain band to pass through the filter. Well, inside the SINAD meter, it does the exact opposite. After it takes this measurement, it then passes that signal through a notch filter. The notch filter notches out, or it blocks, that 1 kilohertz audio tone. So after it's blocked that out, the only thing that's left over is noise and distortion. Now your distortion actually would be, like if you see a little bit of a line here and here, there might be some, let's say, like phase jitter in your signal. Your audio amplifier circuit is causing audio distortion, which is actually causing the tone to actually change a little bit. That's going to show up, because that's distortion. That frequency shift is going to be outside of that notch filter, and it'll be in this measurement. And then it's just, again, like up there, it's just a mathematical formula. The first measurement you take is the signal plus noise plus distortion, and then when you take this measurement, you're measuring the noise plus distortion. It's just simple math. You divide. And that is expressed in dB SINAD. So it's fairly simple. And I'll show how that's done on a communications test set after we get done with this. Actually, let me pause the video, get a drink. I can feel my throat starting to dry out here. I don't want to go into a coughing fit. Had a few chugs of coffee. So, next thing are 2 things that you might find in a manual. Good, even owner's manuals, if they have specs listed in them. Good manuals or manufacturers that are extremely proud of their products will occasionally have either THD or THD+ noise measurements. Now, this isn't so much RF. This is more what you're measuring is the actual audio distortion. Now, this it's right in the name, harmonic distortion. So, THD is a measurement of harmonic distortion and is defined as the ratio of the sum of all harmonic components to the power of the fundamental frequency. So, if we were to look at on a spectrum analyzer, now this would be a spectrum analyzer in the audio realm, but just like a RF spectrum analyzer over there, you'd have, let's say over here we have voltage. So this is actually something you can do if you have a spectrum audio, spectrum analyzer that measures down into the audio range. You can take these measurements and you can calculate THD with a calculator. Do it longhand, takes a long time, but if you have a scientific calculator, and down at the bottom of this, I'm going to show you how you can actually use a calculator with nothing more than taking these actual measurements. But remember, harmonics are doubling or triple, quadruple. But so again, we're going to have 1,000 hertz, but the harmonics, or the second harmonic of 1,000 hertz is going to be 2,000 hertz. And then you're going to have the third harmonic at 3,000, and so on. 4, 5, 6, 7, 8, 9,000 hertz, or the ninth harmonic. Now, I just drew this little chart here, and I have a little kind of like purple line here. So this represents the signal we want. This is our 1,000 hertz audio tone. But anytime you amplify something in audio amplifiers, you end up with harmonics. It's just like with RF amplifiers. So, like in a CB radio. Back in the day, back when television was still analog, when a trucker drove past your house, if he had a butchered radio, when it had been to a hack shop with modulation limiters clipped and whatnot, when he would key his microphone and he was talking, he could wipe out your television. The reason is that was television. Certain frequencies are at the second harmonic of CB frequencies, and by them modifying their radios, they're trying to get more power out. What they were actually doing is just creating more energy in the second harmonic. It's not doing them any good. Well, it's the same thing with audio. This isn't doing us any good. This is the signal we want to hear. This is the stuff we really don't want to hear. Now, there are times you do want harmonics. That's usually in instruments, so stringed instruments, or even wind instruments. It's the reason that let's say an acoustic guitar sounds different than a floor bass. It sounds different than a violin. They can all produce a 1,000 hertz tone, but they all sound completely different. The reason they sound different is they have different harmonic components. So the guitar may have the 1,000 hertz tone, but may have a really huge third harmonic, where the violin might have a huge harmonic, let's say at 4,000 hertz, and I have one here at 2,000 hertz or something. That's why they sound different, because the way they resonate, the bodies of the instrument resonate, they're creating harmonics. But when you're trying to just amplify a signal, you don't want those harmonics. You want to hear what's actually, it's already been recorded, let's say, or, in voice communications, we don't want to hear my voice at 1,000 hertz, 2,000, 3,000, 4,000, and all these different harmonics. This is the measurement that measures all of that junk we don't want. So using this little chart, so in the above example, we have a fundamental frequency of 1,000 hertz, and the span showing up to the 9th harmonic, or 9,000 hertz. And if we actually take measurements, so I have this scale here set from 0 to 4 volts. So if we were to take measurements at each one of those peaks, and this is just an example, but like I say, there's no reason you can't actually do this. Just hook up an instrument and you can actually just take these measurements. You can move your peak marker from peak to peak to peak and take measurements with a spectrum analyzer. And that's what it looked like, and when you wrote them down, this is what you would have. You'd have your fundamental frequency at, let's say, 3.65 volts, the second harmonics at 0.62 volts, and so on. And it's usually going to decrease the farther out you get in harmonics. It's usually going to be less and less and less. So the formula for calculating THD is defined as the ratio of the equivalent root mean square, RMS voltage, of all the harmonic frequencies from the second, so from the second harmonic on. So basically to infinity, over the RMS voltage of the fundamental frequency. Now, like I said, we're only measuring out to the 9th harmonic because, like you can see here, there's nothing measurable even out past the 7th harmonic. But mathematically on this formula, and don't let formulas like this scare you. Like I say, it's if you can use a calculator, you can do these calculations. Some of these symbols can get a little scary. They don't need to be. Like this symbol right here, basically all that is a summation, is what that stands for. Okay, so N equals 2. So that's the first thing we're going to be measuring from the second harmonic, and that is the infinity symbol, because actually you'd be measuring out to infinity. But like I say, in reality, we don't have anything measurable out any farther than the seventh harmonic. So that's why actually all the farther we need to do. We don't need to go to infinity. There's nothing measurable past the 7th harmonic. And then I can use the amplitudes up here instead of voltage RMS, just because the way the math works out, because it will cancel out. So I can use these voltage measurements instead of the actual VRMS because they're going to cancel out. And there's the formula. So, if you have a scientific calculator, you could turn on your spectrum analyzer, move your peak marker from peak to peak to peak, take the actual amplitude measurements, and then with the scientific calculator, you could just punch this in, and it's fairly simple. So let me try and just move this out of the way. You see the display? Yeah, I'm trying to get it so there's no glare on the display. Try and get this all in view. Show you how you actually punch this in. Okay, so we want to start off with a fraction there. Come back. So we have 0.62 squared plus. Now, you got to remember, I said this is a summation. So you're going summation meaning everything between the second harmonic and infinity. We only have measurable to the 7th harmonic. So the sum of all of those measurements there, from the second harmonic to the 7th. So 0.62 squared plus 0.5 squared plus 0.38 squared plus 0.25 squared plus 0.18 squared plus 0.09 squared, and then at the bottom of our fraction we're going to have the measurement taken at the fundamental frequency, which was 3.65. So 3.65, and you can see this is absolutely horrible. This is actually horribly distorted. So the calculation comes out to 0.25 727, blah, 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 and on probably into infinity. But, and it just moved the decimal place over 2 places, and that gives you the percentage THD. So 0.257, blah, 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 move the decimal place over 2, gives you 25.7% total harmonic distortion. Yeah, it's absolutely horrendous, but you got to remember, the reason it's so bad is because you're not just comparing the difference between the second harmonic and the fundamental. You're summing. That's where it's the sum of all of these harmonics. So that's all of these voltages measured, basically, and then compared to that. That's why it's horribly distorted, because you're measuring all of those harmonics. And that's all total harmonic distortion is. But like I say, that's what you're measuring. And I can, again, on communications test set, once I get that fired up, I can show THD measurements, and actually the next one we're going to do THD plus noise measurements. So actually the next one is, and actually the last one we're going to talk about is going to be THD plus noise, or total harmonic distortion plus noise. This is another method of measuring THD, but unlike THD, the only measurement, or THD only measurement, where it's only a ratio of harmonics to fundamental frequency, the THD plus noise measurement also measures noise. So again, we're accounting for noise, and that's a good thing, because we want to try and accurately depict what the output of a radio is, and noise is a fact of life. So you want to try to take that noise, or like in a SINAD measurement, the distortion. You want to try and throw all that into the mix and come up with a measurement that represents that really well. This measurement can be done with, again, nothing but a voltmeter, capable of measuring to the highest harmonic. So, actually, that voltmeter right there would be fine, because actually I even have a label on there. That meter can accurately measure from 5 hertz to 1 megahertz. So, in the case of measuring, this signal here, the highest frequency, actually only the 7th, because that's the highest harmonic where there was still measurable voltage, is only, 7,000 hertz. So that meter is perfectly fine. 7,000 hertz, that one over there measures to 1 megahertz. To the highest harmonic. And now, the only problem is you also need a pair of filters for this, because that's what this does. So, and this one is kind of a good comparison to the SINAD measurement, where it's using a filter. Capable of measuring the highest harmonic, and a pair of filters. One notch filter and one bandpass filter. So again, we're talking about filters. The first measurement it's going to take is going to be, you're going to have your signal source. It's going to pass that through a notch filter. So, just like in this one, it's going to notch it, and it's going to take a measurement. And then it's going, so that's our VRMS without the fundamental. So the fundamental being 1,000 hertz. So we've notched that out. That's not being measured. It's going to take a voltage measurement there, and that's going to be the voltage measurement of all of these summed together. So kind of like our formula right here. It's a summation. You're just doing it with a meter instead of actually using a spectrum analyzer and measuring each individual peak. But like I say, the advantage here is it's including the noise, because there's going to be other little peaks in here probably in between these harmonics, and that's going to be the noise. Well, you can hear that noise too. This formula here does not take into account that noise, where this one does. So but it's taking a measurement. So you're basically feeding a signal in, looks like that. It notch filters that peak out, and it measures the voltage of everything, basically everything that's left over. It then also passes that same signal. After it takes that measurement, it passes it through a bandpass filter. Now the bandpass filter, the only thing it's going to measure is going to be the peak, because it's a band pass. It's only going to pass, let's say, that 1 kilohertz audio tone. And it's going to take another measurement. And that's going to be what's on the bottom of the formula here. And that's it. It's just 2 voltage measurements. One that's measuring everything except the signal that we want, and the other measurement here goes through the bandpass filter and measures only the fundamental frequency. And it's just a ratio. That's it. And again, like I say, I like this one because it includes noise. Where this one's doing some fancy, and it takes actually fancier equipment to do this measurement than it does this one here. This one you can just do it with a voltmeter and 2 filters, where this one you need to be able to, spectrally be able to measure all these different peaks. And like I say, this just represents it to me. It's kind of like the difference between signal plus noise to noise and SINAD. THD plus noise is, to me, is a better measurement than THD, because this only gives you the harmonic distortion. This one gives you the harmonic distortion and the noise. So it better represents what's coming out of your speaker. Same thing here, signal plus noise to noise versus SINAD. This doesn't account for distortion in that audio signal, so if there's any frequency jitter in that audio tone, where the SINAD measurement does. So it's giving you more information. That final result that you end up with is more meaningful because it's measuring, it's calculating more. There's more things included in that measurement. But that's pretty much it. So let me get the papers out of the way here. I'll go grab a, I don't know, probably whatever radio I see that I got sitting on the shelf that has a label on it that says it works. And we'll get that hooked up here, and I can actually show you what some of these measurements, what they look like on, on a real radio, hooked up to a communications test set. So let me stop the video again, and I shall return. Okay, so first radio I grabbed off the shelf is a Untitled Grant. Looks like I bought this in October 2015. Paid $45 for it with shipping. I always put notes on radios when I buy them. Works fine and appears to be 100% stock, so no modifications. And we'll just use this for a sample radio. So I have this connected to the communications test set. It's going to be feeding in, and we're on channel 20, so it's feeding in a signal at 27.205 megahertz. So 1,000, and modulation is 1,000 hertz at 30%. And you'll see people take measurements at 100%. Matter of fact, that's something I saw on one of those questionable videos. They were giving SINAD measurements with 100% modulation, because they said, well, the 30%, you don't talk at 30%. You're going to be talking more at 100% modulation. No, you're not. The reason they pick 30% modulation, if you look at, and actually I can do that with this communications test set. I can take power measurements over time, okay? But that's the problem. When you're talking, I'm talking right now. If you look at that on an oscilloscope or on a spectrum analyzer, it's very rarely reaching peak or 100% modulation. Matter of fact, peak reading watt meters, that's why they have to have a special circuit in there that can hold the needle, or if it's a digital readout, but it can hold that peak measurement, because it stays at that peak for such a short duration. The average modulation when you're talking, like I'm speaking right now, if I was to take a measurement of my voice and we set a peak level, I would only reach that about 30% of the time. The average modulation, coming out of my mouth is only 30%. That's the average. That's why they pick 30% modulation to take all these measurements. So when you look in service manuals, they always tell you, you're setting it the S meters, when you're doing sensitivity tests and whatnot, they always say it's 30% modulation, because that is the average voice modulation, because it's actually so infrequent. You're only reaching those peaks very, very short durations and not very often. You're more or less, you're down at, in that average, it just averages out to about 30%. So that's why they make that the specification. So yeah, anybody gives you SINAD measurements at 100%, they're completely meaningless. No one talks at 100, even if I yell at the top of my lungs nonstop. That's still not 100%, because it's at an audio frequency. So it's only going to reach a peak every once in a while. It's a sine wave. Yeah, like I said, you're never going to be at truly 100% modulation all the time when you're talking. So we just need to make sure that's clear. Let me get the camera swung over here. Get her level up a little bit. Okay, so what we're measuring, so actually the test setup. So the external speaker jack in the radio goes to a speaker, so you can hear it, And then there's also a sample then comes off of that and goes in through this connector right here. And actually, if you look over here, it even basically lays out a roadmap for these connectors. And we're attached to Analyzer 1 audio frequency in. So don't pay any attention to this one here. This one will do 2 measurements at the same time. We're not using Analyzer 2. We're going to be using this column right here, Analyzer 1. And right now I'm feeding in an S9 signal level, and actually it looks like the radio is, I'm looking at the signal meter, the needle is pegged far right, so yeah, it's definitely, the S meter is definitely out of calibration. It should be resting at S9, because I'm feeding it minus 73 dBm, but I'll turn the volume up. I don't want to turn it up too high, because you won't be able to hear me talking over the actual sound, but this is the actual frequency, so I'm feeding in a like I say, it's modulated with 1000 hertz, and that's what this is measuring. This is actually a frequency counter, so it's measuring the audio frequency coming out of the speaker and being fed, that audio signal, the sample off of the speakers coming in here. We can see our THD+ noise is at about, hovering around, it's peaking at like 3.8%, 3.9 maybe. It's getting close to 4, or it's, somewhere between 3.5% to 4%. And our SINAD measurement at 1000 hertz is bouncing around between 28 to 29. Of course, we're going to expect it to be a lot better than, 12 dB because we're at such a high level. If I increase the input into the radio even more, I'll just crank the signal level up, to an insane signal level. You can see, the size. So I'm actually feeding minus 35 dBm into the radio right now. A massive needle bending signal. Yeah, you can see it's 32.7%, or around 32 dB SINAD. And you can see our distortions come down a little bit, THD+ noise. And we can also take THD measurement. So this is total harmonic distortion. Okay, so just like in that graph I showed you, now what they're using here is this left column here is calibrated in dB. It uses the tone that we want to hear, that 1000 hertz tone is set as the 0 dB reference level. And then these are the second, third, all the way out to the 9th harmonic. So 2000, 3000, all the way out to 9000 hertz. And then, just like I showed with the formula, it's just the communications test set does that internally. It's a computer inside with a hard drive, but it does the math. And you can see there's our measurement right there, around 2.2, fluctuating a little bit, but around 2.2% THD. Or around minus 33 dB THD. Now, if I turn the signal down now, the input signal actually into the radio, what we're looking for is that magic 12 dB. Because 12 dB, it's commonly, and let me turn the volume down a little bit. 12 dB, the reason they pick that is 12 dB, now you have to remember, this is a 1000 hertz audio tone. When you're talking, there's a lot more frequencies than 1000 hertz coming out of your mouth. But they pick that because it's the center, it's approximately the center of the normal human voice range. And I'm trying to think how to describe this without getting too technical. Like I say, it's almost impossible for an instrument to measure distortion on complex waveforms like human speech, because the frequency is continuously varying from the lowest frequency, so whoa, way down there, up to really high frequencies. It's hard for it to measure continuously changing it because it doesn't know what to measure at any given time. That's why we use a solid 1000 hertz audio tone. It uses that as the reference level. It knows 1000 hertz is the modulation into the radio, and it wants to see what comes out. But so now let me, like I say, start to turn down the input signal into the radio, and you're going to see that number dropping. But it's agreed that 12 dB is basically the point where you can still have clear two-way voice communications. What I mean by that is, once you start to get less than 12 dB SINAD, you start to have trouble understanding what somebody's saying. You'll start missing words, or they're starting to cut out a little bit. You can't quite tell, what they're saying. Where at 12 dB and above, it's just like listening to me talking now. You can clearly hear everything that I'm saying. You can understand it as long as you understand English, hopefully. But that's that 12 dB point means. 12 dB, absolutely. There's basically no chance of missing a word, because it's not going to be blocked out by noise and distortion, where once you get below 12 dB, you're still going to hear it, and you're still going to understand what they're saying, but it's going to start to get to that point where it starts to get distorted, you start missing segments and whatnot, and and the lower it gets, the harder it is to understand. So I'll keep turning the signal down here now, and you're going to see we're going to reach a point where all of a sudden it's going to start plummeting. We're already down to like 20... down to 19. Now, you'll notice the distortions also, or the THD plus noise is also starting to skyrocket. As this number falls, because dB, or dB SINAD is what they call a positive going measurement, the higher the better. THD plus noise, or THD, the higher the worse, because that's actually the percentage of distortion. And I'm just going to keep turning down until we get right around that magic 12 dB point. We're really close right there, not dropping below. Yeah, so right around there. So turn it up maybe a hair. I'd call it right around there is the 12 dB point, and I'm feeding the radio with a minus 109.4 dBm signal. So that's good. The radio is receiving fine, considering how old it is. It doesn't have any modifications, and probably hasn't had an alignment since it left the factory. And you can see, but THD, and I'll turn it up even more so you can hear it. But you can hear how much background noise and hiss there is in that. And you can see the THD plus noise is up around 23, bouncing up as high as 26%. And if we look at THD, or that was THD plus noise, this is THD, you can see that's actually still not that bad, THD, but like I say, this is the THD measurement does not take into account noise. That's why this one hasn't really changed. The power levels have not gone up in the harmonics. So the THD did not increase. THD plus noise skyrocketed because this measurement includes the magic N, or noise, where this measurement is only measuring 2,000, 3,000 hertz, the power at 4,000, 5,000, and at, on out to 9,000 hertz. Those are the only measurements being taken, and they're actually right up here. Move the camera up just a bit. You can actually see the actual numbers up here in dB. It's only measuring at those specific frequencies. THD plus noise accounts for all that other, the hash and trash, and that's why that measurement looks horrible. Like I say, that's why I prefer THD plus noise, and I prefer SINAD, because it's accounting for where this one accounts for distortion, and this one accounts for noise. So that's it in a nutshell. And you can actually, I can just let's see, grab a different BNC cable here, and I can show you what's a good signal look like. So this one, what we can do is we can just actually measure the signal generator built into this instrument right here. So we just disconnect that, and let's see, generator 1, audio frequency out. So at this jack, it's going to be putting out 1,000 hertz. And we're just going to feed it right back into the instrument. And we can see what a pure... And that's another thing I like about these. These communications test sets have precision signal generators, the audio signal generators. They're called low noise. And I can even demonstrate that if I turn on another signal generator. So I'm going to... Actually, what I'm going to do is I'm going to fire up the Rigel signal generator over there. We'll take some measurements of the signal coming out of this one, and then we'll measure the audio signal coming out of that signal generator, and you'll be able to see, even just using signal generators, the signal, the audio in this one is more pure than that one. But we can, again, we can actually measure that with instrumentation here and show that the Rode and Schwartz, being a much more expensive instrument, you would hope it would be a better signal generator, but we can actually measure that. So okay, now you're not going to hear it because this cable is quite literally just looped the out right back to the input. But you can see that the SINAD is 85.3 dB SINAD. Amazing! You can see the THD plus noise, 0.01%. If we measure THD, you can see 0.0%. Just bouncing. Occasionally it bounces to 0.01. And the reason, again, this one's going to be lower is because this one is only measuring the harmonics, where if we come back to this one, you'll see this one stays at 0.01 all the time. It never goes to 0.00 because there is a little bit of noise. Just the coax cable, there's going to be some noise leaching into this cable. And so you can see there's a little bit of noise there. Then you can see the frequency, it's exactly 1000 hertz. Now let me just set up the Rigel over here. Let's see, I want to make it channel 1, sine wave. Let's see, frequency 1 kilohertz. Amplitude 1. So I'm going to, I need to disconnect the output. So what I'm going to do is disconnect the output from the signal generator in this one, which is what we were measuring, the actual signal generator. I'm going to hook that up to the Rigel, turn the output on, and we come back over here and we can see it's not as good. And that's exactly what I would expect. You're comparing the Cadillac Rode and Schwartz to it's not like it's bad, but the Rigel is nowhere close to the quality of something like this, and you can see that here. Our THD has gone up. It hasn't gone up much, but it has gone up to 0.02%. You can see our SINAD has dropped off considerably. It's now down in the 70s. It's around 76 dB SINAD. And THD, that's now a steady 0.01% instead of pretty much staying at 0.00% and only occasionally fluctuating to 1 or 0.01. So, well, like I say, that's, again, we can measure that. We can compare the audio signal generators in this instrument to another instrument and see that this one has a better signal generator. It's more pure with less harmonics, less distortion, and less noise than the other one. So I hope this has maybe helped to clear up some of the confusion, some of the outright false stuff that's out there. Like I say, there's just some BS floating around out there. It basically comes down to this, people. If somebody tells you they can take something like this, it doesn't even need to be this. It can be a brand new radio. It can be an old tube type radio. It doesn't matter. It can be a CV. It can be an amateur radio. It can be a walkie-talkie. I don't care. But if what they're telling you, they're gonna do something magical. They're gonna sprinkle some of their fairy dust on that radio, and it's gonna do something that sounds too good to be true. Guess what? It's probably too good to be true. So, don't be fooled by people's marketing. And if when you see them give specifications, they say this receiver's sensitivity is, make sure that they're giving it at the industry standard. So, if they're going to give you the SINAD measurement for this radio here, they should be saying something like the SINAD, and actually it was, what was it? What did I say? Minus 109, I think, is what we just measured on this one. I think it was minus 109 point something dBm for 12 dB SINAD. That's the measurement. And you should use 12 dB. If they're giving you a measurement at 10 dB or at 20 dB, then you can't compare them. 20 dB is a much better, it's a much louder signal than 12 dB. Just like 10 dB SINAD is lower. That's a lower signal quality. use the same standard, then you can compare one radio to the next. Same thing with signal to noise, THD measurements. Make sure they're giving, like I say, most service manuals, like for signal plus noise to noise ratios, they're going to tell you to set the radio's output, so that means turn the volume up until you get, and that's the nice thing actually like about that BK1040 over there, it has an audio watt meter built into it, and I also have other audio measuring instrument that's actually a audio amplifier instrument right there. It measures power, it can do all types of distortion measurements as well, but it has a built-in watt meter. But like I say, make sure that when they're giving you, if someone gives you a signal plus noise to noise ratio measurement, or if you're going to do one, make sure you look in the service manual, because it's going to state, whatever their standard is. If they have, let's say it could be a really good standard, like 0.5 microvolts for 10 dB, or it might be 2, or whatever it is. But that's the standard, and they're going to tell you the audio volume should be at a half watt or 1 watt of audio power. So that's how much power is being burned up in the speaker. But like I say, that's the reference. That way you know that that's basically, let's say, a quarter or a half volume, or like at a third volume of a radio. And then every other radio is measured at that exact same, you're using the same set of standards, the same test procedure, taking the same measurement. You can then compare the measurement for this radio, for a radio that was produced today, and you can also compare those measurements with a radio that was made 80 years ago. As long as the same conditions are used, the same load, using the same type of measurement at the same power levels, you can then compare measurements that one person does on a radio to, in my case, the opposite side of the planet. So let's say somebody else has a radio they say receives better than this one. They're in China. But as long as they're using the same standards with the test instruments set up the same, and we're using, like I said, that's the main thing, is the reference. You go changing things, you can't compare them anymore. And I've even heard people say, yeah, the sensitivity on a radio, they're not even giving a measurement. They just say the sensitivity on a radio is minus 130 something dBm. What's that mean? What does the sensitivity is, let's say, minus 130 dBm? What does that mean that the sensitivity is minus 130 dBm? You can hear it with your ears? I guess. Because I've heard people who say, well, you see, I can still hear the signal. Yes, but that's your ear's not calibrated. You can't take a measurement with your ear. I'm sorry, people. You could almost refer to my ears as calibrated. I've dealt with audio most all my life. I have I can discern very slight changes in audio. I'm really good with stuff like that. But even my ears, I can't take measurements with my ears. I can't listen to something and say, that's at exactly this frequency, or it's at this level, or whatnot. You need instrumentation. So I hope that helps. Like I say, this might help to clear up some of the confusion about what these measurements are, how they're done, what they look like. Like I say, there's only so much you can do. No matter what you do to a radio, there's going to be a limit. It just can't hear below that. There's a lot of noise generated inside the radio. Be surprised how much. Now, granted, manufacturers do their best to try and eliminate noise sources inside the radio, and they use filtering to eliminate a lot of the birdies and a lot of, like I said, cross modulation and distortion and harmonics that are produced inside the radio. They do their best to eliminate that, but you can see the radio with a huge signal going into it. The highest dB rating we got out of it, I was feeding like minus 35 dBm into this radio, in through the coax jack, a modulated signal. And the SINAD, the highest SINAD measurement we had was 30 something. It was like 30, 32, 33 dB SINAD. That's the best we could get out of this thing. We hook it up to another signal generator, or to the signal generator in the same instrument, and you can see our SINAD was in the 70s or even in the 80s. Massively better. That's because it's a pure signal, where it's gone through it's been transmitted through the air, it's got to go through all the RF amplifiers, it has to get demodulated, it goes through a couple different IFs, then it has to get then that audio signal, once it gets demodulated, has to be amplified by the audio amplifier. Again, all of these things are creating distortion and harmonic, energy in the radio, and that's why you can only get, with this one, like I say, it was around 30-something dB SINAD. But like I say, there's only so much you can do to eliminate a lot of this noise. Some of it, without superculling, you're just never going to, you can't exceed that level of sensitivity without having basically limitless funds, like a government agency, or lots of backing from rich people. But like I say, I hope this helps. Also hope I hope my description of the different power and voltage measurements, they all mean exactly the same thing. You just need to be really, really careful when you're stating stuff like this, or when you're doing measurements. Because like I say, this one guy is doing, he's setting signal. In other words, when he's done an alignment, he sets the signal meter, right here on the radio. He's feeding minus 67 dBm into the radio and setting the meter to S9. That's wrong. That's too high of a signal. You have to remember, it's minus dBm, so that's negative going. Minus 67 dBm is a much higher signal than minus 73, because you're in the negative, so the lower you can make that negative number, the higher the signal is. But that's, like I say, you need to be sure that you're either talking EMF or under load. That's why I just don't use microvolts anymore. You'll occasionally hear me say it because a lot of people are familiar with those, but when I'm actually working on a radio, I never use microvolts. I don't have to worry about mistakenly using a measurement that's in either electromotive force or unloaded or a loaded measurement. dBm, that's what's so fantastic about dBm. There's no mistaking it. It's always at load. That measurement is always taken into a 50 ohm load. There's no making the mistake of using unloaded or loaded voltage measurements like over here. So I hope that helps clear it up. Like I say, you can go to Mini Circuits. I think it's minicircuits.com. It's not even on this card, but that's where this was. Actually, this was printed out and shrunk. I shrunk it down and laminated it. But you can get the dBm volts watt conversion chart from Mini Circuits. You can go online and find these charts. There's lots of these online. This one, if you specifically type into like the Google Monster search engine, type in S points for frequencies below 30 megahertz, or you type in S points for frequencies above 30 megahertz, you will find the page that these two charts are on. I like these the best of all of the charts that are online because they give you so many different ways of measuring. Where most of them are just going to show you the S meter and either maybe dBm, or they might show you microvolts. But like I say, the one thing this chart does not have on it is EMF. You have to remember, this voltage level right here, that's terminated 50 ohms. Most service manuals, especially on CB radios, if they give you a microvolt level for the input into a radio, it's going to be EMF, unloaded. So, if you do print out one of these little charts, you might want to do the same thing I did here and write microvolt EMF, and then write down these same levels right here. And that way you can see. That way if you use a service manual and it says 100 microvolts EMF, you can look that up on this chart and say, oh, yep, that's S9. Or, if it's 50 microvolts terminated into 50 ohms, but you can, like I said, write that on there. That'll help to alleviate some confusion for you, probably. So there you go. Hope that helps. I hope you learned something, and I hope I didn't confuse you more than you were already confused before.